Do you truly believe that there could be a planet out there? One that's like our Earth, but older, bigger? Is it just imagination? Or does something like this really exist? Just imagine. You're standing on top of a dusty mountain. All around you silence. No birdsong, no rustling leaves. Above your head, a hazy bluish sky floats, with a strange sun, older than our own. But somehow, it still feels familiar. The ground beneath your feet is firm, a little coarse. Yet there's no sign of life. You know, this isn't Earth. This is Kepler 22b. It would take 1,400 years to get there. So is it even possible? No, this isn't some fairy tale planet. It's real. When NASA first confirmed its existence in 2015, scientists said, "It's Earth's older cousin, a planet that looks just like our own, orbiting a sun much like ours, receiving a similar amount of light and warmth, with similar size structure. Even the length of its days is nearly the same." And yet the question remains, can we live there? Can we create a new Earth for the generations to come? In this series, I'm Eve. And I'll take you to worlds we may never reach physically, but can still explore on the wings of imagination. And behind that imagination, there will be science, logic, and a pinch of wonder. Welcome to Tales-ByEve, where we uncover the truths hidden behind our dreams. In this episode, we'll ask, could Kepler 452b truly become our second Earth? Or is this dream just that, a dream? Then let this cosmic conversation begin.
Okay, let's unpack this. We are diving deep into one of the most talked about exoplanet discoveries, Kepler 452b.
Yes.
Back when it was announced, 2015, the headlines just exploded. Earth's cousin, even Earth 2.0.
They really did. Big, splashy headlines. But, what's behind the hype? What did the science actually say?
Exactly. What did the scientists using Kepler really find?
Well, that's what we're doing today. We're going straight to the source material. We've got the original NASA discovery paper from Jenkins and his team.
The 2015 one.
That's the one.
Yeah.
And then there's a really interesting follow-up study from 2017, Silva and colleagues, looking at habitability with climate models.
Okay.
And some broader stuff, too, from folks like Ethan Siegel and Hawk Misra, putting it all in context. The search for Earth-like worlds, why we're even around a star like our sun.
Right. So our mission for this deep dive is basically cut through those headlines. We want to figure out what Kepler 452b actually is.
How sure are we it's even a planet?
Yeah, sure. What are its key features? Could it actually be habitable? Like really habitable?
And what does this one planet tell us about the bigger picture, the search for life elsewhere?
Okay. Ready to jump in?
Absolutely. Let's do it.
All right. So basics first. How did they even spot this thing? It came from the Kepler Space Telescope, yeah.
That's right. Kepler. Its whole job was using the transit method, staring at one patch of sky for years.
Just staring.
Monitoring hundreds of thousands of stars, looking for these tiny, tiny periodic dips in their brightness.
The dips being a planet passing in front, blocking a little bit of starlight, like a mini eclipse from really far away.
Exactly. So for the star we now call Kepler 452, the team went through 4 years of Kepler data from 2009 to 2013.
4 years of data, just patiently watching.
Incredible amount of data.
Yeah.
And in the light curve for Kepler 452, they found 4 distinct dips.
Only 4. Over 4 years, that sounds like a long orbit.
It is, a very long orbit. The time between those dips, the planet's orbital period, turned out to be 384.843 days.
Whoa.
Yeah. At the time, that was the longest orbital period for any small transiting planet Kepler had found. Because the orbit's so long, they only saw it cross 4 times in that main observation window.
384 days. That is almost exactly an Earth year.
Remarkably close, yeah.
Yeah.
And the transits themselves, really shallow. Dimmed the star's light by only about 200 parts per million.
200 ppm, that's what, 0.02%?
Tiny.
Tiny. And each crossing, each transit, lasted about 10.5 hours.
Okay, 4 shallow dips once every 384 days.
But, like you said, just seeing a dip isn't proof, is it? There must be other stuff out there that can mimic a planet.
Oh, absolutely. That's the critical next step. Validation. You have to be really sure it's a planet orbiting that star and not some kind of, well, cosmic imposture.
Imposters? Like what?
Could be lots of things. Maybe 2 background stars orbiting each other, an eclipsing binary that just happens to line up with the target star. Or maybe a bigger planet orbiting a different, fainter star in the background, but it looks like it's coming from the target star's pixel on the detector.
Right, so how do you rule all that out? Sounds complex.
It is. They have a whole battery of tests. Really rigorous stuff. Checking the shape of the dips, comparing different transits.
Like odd versus even transits. I think I read about that.
Exactly. The odd-even test. They compared the depth of the first and third transits to the second and fourth. For 452b, there was no significant difference. That strongly argues against it being a background eclipsing binary.
Okay, 1 check passed. What else?
They do statistical tests, like a bootstrap analysis, comparing the signal strength to the actual noise in the data. Kepler 452b signal was detected at 9.7 sigma significance.
Which is good.
Very good. The false alarm probability was incredibly low, way below the mission requirement than their centroid analysis.
Checking where the dimming happened.
Precisely, and making sure the dimming is centered exactly on the target star, Kepler 452, and not slightly off to the side, which would indicate a background source. They checked pixel by pixel, confirmed. The signal came right from Kepler 452. They also checked for contamination from other nearby stars, optical ghosting, all sorts of instrumental effects. They ruled those out too.
So lots of checks, but the big one is often this blender analysis, right?
Ah, yes. Blender. That's a powerful technique. They basically simulate thousands of realistic false positive scenarios. Those background eclipsing binaries, background stars with planets.
They make fake data that looks like a false positive.
Exactly. Then they compare those simulations to the actual Kepler light curve. They ask, how likely is it that one of these blend scenarios could perfectly mimic the signal we saw?
And for Kepler 452b?
The outcome was pretty definitive. The analysis showed the planet hypothesis was favored over any of those blend scenarios by an odds ratio of 424 to 1.
424 to 1. Okay, that sounds like very high confidence.
Extremely high, far beyond the threshold Kepler required to say, yep, this candidate is a validated planet.
Okay, so we're very confident it's a real planet. Now, to really understand the planet, we need to know its star, right? Kepler 452 itself, what's the scoop there?
Absolutely essential, yes. The star's properties tell us about the planet's environment. And crucially, they let us figure out the planet's size from how much light it blocks.
So how'd they study the star?
Ground-based telescopes, taking detailed spectra, breaking down the star's light to measure its temperature, gravity, what elements it's made of.
And what kind of star is it?
It's a G2 star.
Like our sun. The sun's a G2.
Very similar classification, yes. Its effective temperature is around 5757 Kelvin. Surface gravity close to the sun's, and is actually a bit richer in heavy elements than the sun, higher metallicity, as astronomers say.
How does it stack up directly against the sun?
Well, it's slightly cooler, maybe 85 Kelvin cooler, a bit larger, about 11% larger radius based on models, and about 60% more metal-rich. So G2 type, yes, but not identical.
Got it. Slightly cooler, a bit bigger, more metals. What about its age? That seems important.
Very important. By plugging its properties into stellar evolution models, matching things up with theoretical tracks, they estimate its mass at about 1.04 times the sun's mass. And its age at roughly 6 billion years, plus or minus maybe 2 billion years. There's some uncertainty.
6 billion years. Okay, that's a key difference. Our sun's only, what, 4.6 billion?
Right. So Kepler 452 is significantly older, about 1.5 billion years older than the sun.
And that, as you said, probably has implications for the planet.
Definitely. So now we combine the star size with how much light the planet blocked during those transits.
To get the planet size.
Exactly. And Kepler 452b comes out with a radius of 1.63 times the radius of Earth. Give or take a bit, about 0.2 Earth radii uncertainty.
1.63 Earth radii. So noticeably bigger than Earth. Definitely not tiny, but much smaller than Neptune or Jupiter.
Precisely. It falls into that category we often call super-Earth or sometimes mini-Neptune.
Right, that interesting size range.
It is interesting and a bit ambiguous, really. Planets this size could be rocky, like a scaled-up Earth. Or they might have held on to a significant atmosphere, a thick envelope of gas or volatiles, making them more like a small Neptune.
So that size alone tells us it's not an exact Earth twin.
That's a key distinction, yes. Now, its orbit. We already said the period is 384.8 days. The distance from its star works out to 1.046 astronomical units, or AU.
Okay, 1 AU is Earth's distance from the sun, so 1.046. It's orbiting just slightly farther out than Earth is.
Almost the same orbital distance, yeah. And it takes just a bit longer to go around. Incredibly similar orbit to Earth's.
And because we know the star's size and temperature, we can figure out how much sunlight or starlight the planet gets.
Right. The insolation. Kepler 452b receives about 1.10 times the energy flux that Earth gets from the sun today.
So about 10% more sunlight.
Roughly 10% more, yeah. And if you calculate an equilibrium temperature, assuming an Earth-like reflectivity, you get around 265 Kelvin.
265 K, that's below freezing for water, but that's without an atmosphere, right? Like Mars's equilibrium temp is low too.
Exactly. That's just the temperature from balancing incoming starlight. An atmosphere could warm it significantly, potentially allowing liquid water. So location-wise, temperature-wise, less promising.
But composition? Is it rocky? You said maybe not.
That's the million-dollar question, really. The problem is we couldn't measure its mass directly. Radial velocity measurements, which give you mass, are really hard for faint, distant stars like this.
So without mass, you can't get density, and density tells you what it's made of.
Precisely. So we have to rely on statistical estimates. Based on other planets where we do have both radius and mass, scientists have built models.
Mass-radius relationships.
Yeah. And plugging Kepler 452b's radius into those models. Well, the probability of being rocky comes out somewhere between 49% and 62%.
Huh. Basically a coin toss. 50-50, maybe rocky, maybe not.
Pretty much. It's far from certain. And even if it is rocky, being 1.6 times Earth's size, models suggest it might have a different internal structure. Maybe less iron, more silicates than Earth. It's right in that size zone where things get tricky.
Okay. So 1.6 times Earth size, G2 star, similar orbit, 10% more light, maybe rocky, maybe not. Let's talk habitability, the big headline grabber. What exactly is the habitable zone?
So the habitable zone, or HZ, is basically the region around a star, where if you had a rocky planet with the right kind of atmosphere, liquid water could exist on its surface.
Could exist doesn't mean it does.
Right. It's about potential. And there are different ways to define the edges. There's the optimistic HZ, which is wider.
Based on conditions like early Mars or recent Venus?
Sort of, yeah. Looser boundaries.
Right.
And then there's the conservative HZ, which is narrower, based on stricter climate limits, like where a runaway greenhouse effect might start.
And Kepler 452b, where does it sit?
Given its orbit and the star's current brightness, it falls well within that optimistic HZ. It's just slightly inside the inner edge of the conservative HZ, getting that 10% extra flux compared to Earth.
So location, check. Looks good, at least optimistically, but just being in the zone isn't enough, right? That Silva paper went deeper.
Much deeper. That study used a proper climate model, the ESTM model, to really simulate what the surface conditions might be like. They didn't just look at insulation. They varied all sorts of things we don't know.
Like what?
Like surface gravity, how much CO2 is in the atmosphere, the total atmospheric pressure, how elliptical the orbit might be, how fast the planet spins, its axial tilt, how much ocean it might have.
Wow, okay, that's a lot of variables.
It is, and the modeling showed just how crucial those unknowns are. For example, atmospheric pressure and CO2 levels. Huge impact.
How so?
They found that for the planet to have a high habitability index, which they defined in a way linked to detecting biosignatures, you probably need CO2 partial pressure below about 0.04 bar. And total pressure probably needs to be below maybe 2 bar if you have Earth-like CO2 levels.
So if it has a thick CO2-rich atmosphere, maybe like Venus.
That even with only 10% more sunlight, it could easily tip into a runaway greenhouse. Too hot for liquid water, gone.
What about the orbit shape? Eccentricity.
Also critical. We don't know its eccentricity, but if the orbit is too stretched out, too elliptical, the planet could swing between scorching hot and freezing cold, even if the average distance is fine.
Yeah.
Their models showed habitability drops off fast if eccentricity gets much above 0.3.
Right, so steady temperatures matter.
They do. Things like rotation speed and axial tilt also play a role, mainly in how heat gets spread between the equator and poles. It affects what fraction of the surface might be habitable.
So the bottom line from the climate modeling is potential, yes, but heavily dependent on factors we just don't know yet.
Exactly. Location is promising, but true habitability hinges on things we can't measure from just the transit data.
Now, you mentioned Kepler 452, the star, is older than our sun. How does that age factor into the planet's story?
Yeah, this is really fascinating. Because Kepler 452 is older and slightly more luminous now, it might give us a peek into Earth's own distant future.
How so? Stars get brighter as they age.
On the main sequence, yes. Stars like the Sun and Kepler 452 gradually increase their luminosity over billions of years.
So the habitable zone actually moves outwards over time.
It does. And the research suggests that for its first, maybe 5 billion years, Kepler 452b was likely receiving less energy from its star than Earth gets today.
Ah, so it might have spent a long time well inside the conservative habitable zone.
Quite possibly. Billions of years in potentially more comfortable conditions, depending on its early atmosphere and water, of course.
And now it's getting that 10% extra sunlight.
Right. It's still within the optimistic HZ. But the star will keep getting brighter. The models estimate it might remain in the optimistic HZ for maybe another 3 billion years or so.
Before
The increasing stellar flux likely pushes it into a runaway greenhouse, boiling off any surface water.
Which is basically the long-term forecast for Earth, too, as our sun ages, millions of years from now.
Exactly. So in that sense, Kepler 452b isn't just an Earth cousin. Maybe it's like a future Earth, experiencing that increased stellar heating first.
That really changes the perspective, though, like Ethan Siegel argued, calling it an Earth twin is a stretch, given the size difference and the maybe not rocky part.
Definitely not a twin, no. Similar orbit, similar star type, but the planet itself is different. Bigger, uncertain composition, older system.
Does finding planets like this, similar but not identical, change how we search for life? Should we only be looking for exact twins?
Well, that's a huge debate. It feeds right into the bigger picture. If the ultimate goal is finding life, maybe even observers like us, focusing only on finding exact Earth copies around G-type stars like our sun might be, missing the forest for the trees.
Why? Because G-stars aren't that common.
Relatively speaking, no. G-dwarfs like the sun make up maybe 7% of stars. The vast majority, around 75%, are M-dwarfs, those small, cool red dwarf stars.
And we're finding lots of planets around M-dwarfs now, right? In their habitable zones.
Loads of them. Think TRAPPIST-1. M-dwarfs live for trillions of years, way longer than the sun's 10 billion year lifespan.
Okay, so M-dwarfs, way more numerous, live way longer, seem to have rocky planets in the HZ. Shouldn't most life be around them, statistically?
That's the million-dollar question, isn't it? And it's what papers like Hawk-Misra et al. Dig into using statistics and anthropic reasoning.
Anthropic reasoning, the idea that our observations have to allow for our own existence.
Yeah. Basically, if M-dwarfs are so common and long-lived, why do we find ourselves orbiting a G-dwarf relatively early in the universe's history? It seems a bit statistically odd on the surface.
So why are we here then? Any ideas?
Well, the papers explore a few things. One idea is that maybe the physical size of the habitable zone, the actual width of that Goldilocks region, is just smaller around M-dwarfs. Less room for error, maybe a less total habitable real estate despite the stars being numerous.
Okay, so quantity versus quality of the HZ, maybe.
Possibly. Another factor could be M-dwarf habitability itself. Are they actually good places for life? There are concerns about intense stellar flares, tidal locking, maybe early water loss, though these are still heavily debated topics.
So maybe G-dwarfs, while rarer, are just intrinsically better nurseries for complex life.
That's one possibility.
Or
maybe it's about time. If you look across all of cosmic time, those M-dwarfs will be around for trillions of years. The total opportunity for life around them is immense. From that perspective, us being here now, around a G-dwarf that's only middle-aged, that looks even less likely statistically.
So we might just be a fluke, an early bird in a galaxy that will mostly host life around red dwarfs later on.
Could be. A statistical anomaly, like having red hair, as one paper put it. Or maybe the very definition of observer like us is somehow tied to conditions around G-dwarfs or this particular cosmic era. Maybe complex life just arises earlier or more easily here. So finding ourselves here isn't strange at all. It's exactly what we should expect based on our type of existence. It kind of makes your head spin.
Wow. Okay, this has been quite the journey from detection to these big cosmic questions. So let's try and wrap this up. Kepler 452b, what's the final takeaway?
I think the final word is that it's still a landmark discovery, a fascinating super-Earth, Orbiting a sun-like star right around that 1 AU distance, putting it in the habitable zone, it was the closest thing Kepler found to an Earth-Sun system analog in that setup.
And the discovery itself is solid. We're very confident it's a real planet with those basic properties.
Extremely confident in the detection, yes.
Yeah.
But, and this is the big but, its actual surface habitability, that's still a major question mark.
Right. Size puts it in that fuzzy super-Earth mini-Neptune zone, and everything depends on atmosphere, orbit details. Stuff we don't know.
Exactly. Its potential for liquid water is there, but it hinges critically on those unknowns.
And its age gives us that interesting perspective, a system older than ours, maybe showing us what happens as stars evolve.
Yeah, potentially a glimpse into Earth's own very distant future, seeing a planet that's likely been in or near the habitable zone for billions of years, but is now feeling the heat increase.
So it's this one important piece, right? One data point in this huge puzzle of finding habitable worlds.
It really is. Discoveries like Kepler 452b help us figure out how common these kinds of planets are, especially around stars like our sun. But they also push us to think bigger.
Prompting those deeper questions.
Yeah, about where life might really be most likely. Should we be so focused on G-stars? Or should we be looking harder at those incredibly numerous, incredibly long-lived M-dwarfs? It challenges our assumptions.
It really makes you wonder, doesn't it, if life is potentially more common statistically around those ancient M-dwarfs over cosmic time. Are there observers out there right now looking back at our little G-dwarf system thinking we're the unusual ones?